everyone. Welcome back to the lectures in Introduction to Multi-Agent Systems. In today's lecture, we'll study about the solutions of a system of nonlinear differential equations. In the previous lecture, we saw that the state space representation of a nonlinear system consists of nonlinear terms in their differential equations. So, can we always find out a solution of these equations? The answer to that is no. Only under certain suitable conditions on the nonlinearity can we say that the solution will first of all exist. Sometimes it may also happen that there are multiple solutions which exist, which of course is undesirable for us. So we'll also figure out the conditions that can ensure that the solutions not only exist, but are also unique in nature. So let's get started and try to understand how do we go about it.
We know that any nonlinear system can be represented using a state space in a state space form as well, such that x, let x be the state vector, such that x has a dimension of n cross 1. Then the derivative of this x is some nonlinear function of the states x again, t, and u, which is some external input. Now, when can we say that these set of nonlinear equations, so why do we say these set of equations? Because please remember, this is n cross 1. So the f that we have here is also n cross 1. So when can we say that these set of n equations have a solution? Or to put it more technically, when can we say that the solutions of these equations exist? And when is this solution unique? In order to be able to answer these questions, we'll first have to understand the notion of something that's known as Lipschitz continuity. So we'll explain later how Lipschitz continuity can be used to understand the conditions for the uniqueness and existence of solutions. For now, let's try to understand what exactly is Lipschitz continuity. Lipschitz continuity. To understand that, let us say that we have been given some domain space over which the function is defined. Let the domain space be D, which is a subset Rn. Only thing we say is the domain must be open and connected. Secondly, before we actually formally define what is Lipschitz or how to express it for the most general form, let's start by a simpler form where we assume the function f to be given to us as a real valued function, meaning let f be some nonlinear function that's given to us, and we say that this is equal to f of x, where our domain, this x, is actually real valued, just r. Meaning here, every x is real valued. We are just starting with this simpler setup. We will generalize it soon enough. And then write the conditions. F is locally Lipschitz x if there exists some positive real number L or L greater than 0 such that mod of fx minus f of y is less than or equal to L times mod of x minus y. So what does this condition mean? If you observe it a bit more carefully, we can simply rewrite this as mod of x minus f of y divided by mod of x minus y, simply less than or equal to L. If you want to write it graphically, if you want to explain it graphically, then we would say some conditions like this. Suppose this is x and this is f of x. And our function f, say, looks like this. Then let us mark the points. Suppose this is first. Let's mark some points x and y. Say this is x, this is y, and this is f of x. And this these are f of y and f of x. Then f of x minus f of y over x minus y is nothing but the slope of a straight line passing through these 2 points. And the claim is, whatever is the domain that's given to us, over that domain, whenever we construct these, the derivative or the slope of this must always be bounded by some positive number, L. If our function f satisfies this condition, then we say that it is Lipschitz continuous. Let us now solve an example. Suppose f of x is equal to x raised to the power 1/3. Is this function locally Lipschitz at every point in the domain? So what is the domain that's given to us? V in this case again is equal to R. So meaning x belongs to some point along the real line. Is this function, so this is the plot of x raised to the power 1/3. Is this function always Lipschitz, meaning can we always bound its derivative? The answer is no. If we look very closely about the point x equals 0, if we look very closely at x equals 0, then we see that or notice that around this region, the derivative takes very high values, meaning the function is not locally Lipschitz at every point in R. Let's write it. This is not locally Lipschitz. This function here is not locally Lipschitz at every point in Rn. R. However, let us take some point here. Let us this point and only consider the region 1, 2, 3. In this region, is this function locally Lipschitz if this is what our domain is? The answer to that question is yes. We can always find an upper bound on the derivative or upper bound of slope at this point. That's why the function will be locally Lipschitz if we now consider some bounded region away from the origin. Let us take yet another very simple example. Let now our f of x be equal to x plus 2. Now if we try to plot this, then we know that at x equals 0, the value is 2, so it'll, and the slope is equal to 1, so it will be this straight line here. Okay, now is the straight line locally Lipschitz or not? Let's try to figure that out. Suppose we take any points, any 2 points x comma y in the domain. Again, the domain is equal to R in this case. Then f of x minus f of y is equal to x plus 2 minus y plus 2, which is x minus y. Now, let us evaluate this. So, if you remember, we have to evaluate this particular expression and see whether we can bound this or not. Now, this is simply equal to x minus y, the mod of this, divided by again x minus y, the mod of this, meaning this is always equal to 1. Hence, you can see that the derivative or the rate at which this function grows can always be bounded by any number greater than or equal to 1. Hence, we can say that this implies not only within a certain region, but this function is actually, its slope is bounded all through the domain. For example, we saw that while this is locally, the function fx is locally Lipschitz in some region, it is not locally Lipschitz for every point in the domain. Hence, not locally Lipschitz at, there's just one point where it defaults, that is at x equals 0. However, this function is not only locally, but globally Lipschitz. Throughout R, we can bound its derivative. Hence, we say that f of x is globally Lipschitz with L greater than or equal to 1. We can take any L greater than or equal to 1 as its Lipschitz. So all of the examples that we saw here were defined for functions which are real valued. However, in general, when we are dealing with state vectors, we say it is n-dimensional, meaning we should also understand how to talk about Lipschitz conditions when x or and f belong to Rn. So let us generalize those conditions and say Lipschitz continuity in Rn. How do you say it? This is how. So the domain, any domain in Rn, suppose f is our function. This function is, say, globally Lipschitz. Notice that it can be defined similarly for locally Lipschitz as well. So this function is globally Lipschitz if there exists some L greater than 0 such that norm of, so here we have written a very general form of f. It can be a function when we are dealing with the state space scenario. Remember that it can be a function of both t and x and some external input, which right now we are not considering. So let's write t comma y. Norm of this is less than or equal to L times norm of x minus y. Here, x belongs to the domain, meaning x has a dimension of n cross 1. When we say globally Lipschitz, then this condition, it's not enough to write this, but this condition must hold for every x comma y belonging to the domain. Only then we know that the function is globally Lipschitz. It is locally Lipschitz if we take any point and around its neighborhood, we can say that the derivative is bounded. We can quickly look at a couple more examples. Suppose f of t comma x is now equal to t times x squared. Then if our domain is defined as follows: t comma x such that 0 less than equal to t, which is less than equal to some capital T. So the question is this function Lipschitz in the given domain? The answer to this question is no. I leave it for the students to prove why this will not be locally Lipschitz everywhere. I'm sorry, why this will not be globally Lipschitz. It is in fact locally Lipschitz. So let me write it here. It is locally Lipschitz, but not globally. Because over the given domain, we will not be able to find a bound. Similarly, what happens if we now change the domain slightly? Let us do that. Suppose we now say the domain D is in fact equal to some t comma x such that 0 less than equal to t less than equal to some capital T. Along with that, we now also have a bound on how much x can vary. Say some x bar less than equal to x less than equal to x bar again. Suppose this is our domain. Now we see that we have also constrained x to vary between minus x bar to x bar. Hence, this function here can only vary from minus x bar square to x bar squared. Right? This can vary between minus x bar squared, which is nothing but x bar squared again, to x bar squared, meaning it can vary from 0 to x bar squared. As we see that the derivative now can always be bounded. The derivative is f of comma x. It can always be bounded. So is this globally Lipschitz? The answer now changes to yes. Yes. F is globally Lipschitz. Let's call them D1 and D2 in domain D2. This is interesting because we also see that it's the same function. However, as we change the domain in which x is defined, the Lipschitz properties of the system also changes. So the question is, how does Lipschitz continuity help us in defining some properties of the solutions of the nonlinear equations that arise from a state space representation of a nonlinear system? The answer to the question of how does Lipschitz help us is given as follows. Consider the system x dot equals f of t comma x. Then the existence of the solutions is given by this. Let f. We are looking at an unforced system as of now. There's no external input that is appearing here. Let f of t comma x satisfy the following properties. What are the properties? The first is f of t comma x is piecewise continuous in T. This is the first condition. And the second condition says that f of t comma x is locally Lipschitz in x. Suppose f satisfies both of these conditions. Then a unique solution exists for the differential equations. Now, the nonlinear differential equations governed by this, where we have some initial condition given by x at t naught being equal to x0, So this unique solution exists over some t from t naught to t naught plus delta for some delta greater than 0. So this is what, or this is how Lipschitz continuity helps us. We say that f that is given to us is piecewise continuous in t, then it is also locally Lipschitz in x. Under these conditions, the nonlinear equations governed using this. So we can specify the initial conditions here as well. Xt naught is equal to some x naught. Then we know that not only does the solution exist, it is also unique. Again, let's see a very quick example. A few minutes ago, we saw this example x raised to the power 1 by 3. And we saw that near the origin, if we take the domain, or if we take x equals 0, we know that it is not locally Lipschitz there. But let us see, if it is not Lipschitz, then what breaks down? Do we actually get multiple solutions? Let us see. Suppose these are the initial conditions. Now, if fx equals x raised to the power 1/3, then the equation that we get is x dot is equal to fx, which is equal to x raised to the power 1/3. Then we can very easily solve this integration and say that the solution of this differential equation is given by this. Twice of t divided by 3 raised to the power 3 by 2. So this is the solution of the differential equation. If we substitute t equals 0, then we see that we do get x of 0 equals 0. Hence, we see that it satisfies this differential equation. But is this the only solution? The answer is no, it's not. There's yet another solution, which is given as this. X of t equals 0. Notice that this equation also satisfies, we notice that this equation also satisfies a differential equation given here, meaning this is also a valid solution. So what exactly did we find? We found two different trajectories or two different possible solutions for the same differential equation. And this happens because at the origin, the function is not locally Lipschitz, or it's not Lipschitz at that point. Hence, we can conclude that solution is non-unique while it does exist. Hence, we know that Lipschitz continuity is very important for not only the existence, for primarily, so existence is a weaker condition and can be imposed with slightly less strict conditions, but uniqueness requires the function f to be locally Lipschitz in X. So with this, we'll end today's lecture. We have understood when exactly the solution of a nonlinear differential equation will first of all exist and then be unique. In the next lecture, we'll define the notion of stability and understand what are the different kinds of stabilities that are there for a given system. Thank you.